Welcome to this lesson on droplet generation in microfluidics. Today we're going to explore how tiny droplets are created at T-junctions and flow-focusing nozzles, and what physics controls their size and frequency. But first, why do we care about generating droplets? Droplet microfluidics enables us to create thousands of tiny reactors per second. Each droplet can be a separate experiment for drug screening, chemical synthesis, or biological assays. Each droplet acts as an isolated container. Imagine being able to run 10,000 different experiments simultaneously in a device the size of a microscope slide. The applications range from drug discovery, where we test thousands of compounds, to single-cell analysis, where each cell gets its own droplet, to rapid diagnostics. Let's start with the T-junction. This is one of the simplest and most common geometries for droplet generation. Here's a schematic of a T-junction. The dispersed phase, shown in blue, flows down from the top. The continuous phase, in green, flows horizontally. They meet at the junction, and droplets form that flow out to the right. The dispersed phase is the liquid that will form the droplets. Think of it as oil if we're making oil and water droplets. The continuous phase is the carrier fluid. It flows perpendicular to the dispersed phase and sweeps it into droplets. Now let's understand the physical mechanism. How exactly does the dispersed phase break into droplets? Three forces are competing. Viscous drag from the continuous phase pulls the dispersed phase downstream. Interfacial tension tries to minimize surface area, and pressure differences push fluid through the channels. Here we see the dispersed phase entering the junction. The continuous phase exerts viscous drag, pulling it downstream. Meanwhile, interfacial tension acts like a rubber band, trying to pull the interface back and minimize surface area. Here's a question. What determines when the droplet actually breaks off? Is it just time, or is there a critical condition? The answer is that breakup occurs when the neck connecting the droplet to the dispersed phase becomes thin enough to be unstable. The interfacial tension then rapidly pinches it off. The key dimensionless number governing this process is the capillary number. Let me write this down. The capillary number is defined as Ca equals mu u over gamma, where mu is the viscosity of the continuous phase, u is the velocity, and gamma is the interfacial tension. The capillary number represents the ratio of viscous forces trying to deform the interface to surface tension forces trying to maintain it. This ratio determines the droplet formation regime. At low capillary numbers, typically less than 0.01, we're in the squeezing regime. Here droplets are larger than the channel width, and they squeeze through, blocking flow periodically. At moderate capillary numbers, from 0.01 to 1, we have the dripping regime with nice regular droplet formation. This is the sweet spot for most applications. At high capillary numbers, above 1, we enter the jetting regime, where the dispersed phase forms a long jet that eventually breaks up far downstream. Now let's talk about how flow rates affect droplet size. This is crucial for controlling your experiments. We define the flow rate ratio, phi, as Qd over Q circa. That's the dispersed phase flow rate, divided by the continuous phase flow rate. Higher phi means you're pumping more dispersed phase relative to continuous phase, so you get larger droplets. Lower phi means less dispersed phase, giving you smaller droplets. It's intuitive once you think about it. Let's do a quick back-of-envelope calculation to estimate droplet volume. This is the kind of estimate you do before running an experiment. The droplet volume is approximately Qd over F, where F is the droplet generation frequency. If you know how fast you're pumping fluid and how many droplets per second you're making, you can estimate the volume. Let's say we're pumping dispersed phase at 1 microliter per minute and generating droplets at 100 Hz, or 100 droplets per second. 1 microliter is 10 to the negative 9 cubic meters. Divide by 60 seconds per minute to get the flow rate per second. Then divide by 100 droplets per second. This gives us approximately 167 picoliters per droplet. That's a droplet with a diameter of about 70 micrometers. Now let's move on to the second major geometry, the flow-focusing nozzle. This is even more powerful than the T-junction. In a flow-focusing device, the dispersed phase flows through a central channel. The continuous phase flows from two side channels and focuses the dispersed phase through a narrow orifice. The geometry creates a symmetric squeezing force. Flow focusing has advantages over T-junctions. You get better monodispersity, meaning more uniform droplet sizes. You also have better control over droplet size by adjusting the orifice width. Both phases accelerate as they squeeze through the orifice. This creates strong extensional flow that thins the dispersed phase thread very effectively. Let's dig deeper into how viscosity affects droplet formation. This is often counterintuitive. Here's a question. If you increase the viscosity of the continuous phase, do you get larger or smaller droplets? Think about it for a moment. The answer is it depends on which regime you're in. In the squeezing regime, viscosity has little effect because the mechanism is geometric. But in the dripping regime, higher continuous phase viscosity increases the capillary number. Higher continuous phase viscosity means higher capillary number, which means stronger viscous forces. These forces pull the droplet thread thinner before breakup, resulting in smaller droplets. But dispersed phase viscosity has the opposite effect. Higher dispersed phase viscosity resists deformation and leads to larger droplets. Now let's talk about interfacial tension. This is the unsung hero of droplet microfluidics. Interfacial tension gamma typically ranges from 1 to 50 millinewtons per meter for oil-water systems. Surfactants can lower this dramatically. Lower interfacial tension makes droplets easier to deform and break up. This increases the capillary number and can shift you to a different regime. Here's an analogy. Interfacial tension acts like a rubber band around the droplet interface. A tight rubber band means high tension and small droplets. A loose rubber band means low tension, and the droplet can grow larger before breaking. Now I want to show you a powerful scaling relationship that emerges from dimensional analysis. The droplet diameter d divided by the channel width w scales as phi to the power of 0.3 times capillary number to the power of negative 0.3. This is an empirical relationship that works remarkably well. Notice the exponent is only 0.3. This means droplet size depends only weakly on the flow rate ratio. You need to change phi by a factor of 10 to double the droplet size. Similarly, the capillary number has a negative 0.3 exponent. Higher flow velocity or lower interfacial tension gives smaller droplets. Let's work through a practical example that ties everything together. Suppose you want to make 50 micron diameter droplets. You have a channel that's 100 microns wide. You're using an oil-water system with interfacial tension of 20 millinewtons per meter. The ratio of droplet diameter to channel width is 50 over 100, which equals 0.5. Let's say we want a flow rate ratio of 0.1 for stable operation. That means the continuous phase flows 10 times faster than the dispersed phase. Using our scaling law, 0.5 approximately equals 0.1 to the 0.3 times Ca to the negative 0.3. Solving this, we find that the capillary number should be around 0.05. This puts us in the squeezing to dripping transition regime. Now we can solve for the required velocity. U equals Ca times gamma over mu. If the continuous phase is water with viscosity 1 millipascal second, then U equals 0.05 times 20 times 10 to the minus 3 divided by 10 to the minus 3, which gives 1 meter per second. That's quite fast. Let's talk about how fast we can generate droplets. This determines the throughput of your system. The frequency scales as velocity over some characteristic length. For squeezing regime, this length is roughly the droplet size. Typical frequencies range from 10 Hz for slow, large droplet generation up to 10 kHz for fast, small droplets. That's up to 10,000 droplets per second. Here's a question. What limits how fast you can generate droplets? Why can't we go to a megahertz? The answer involves multiple factors. Channel resistance increases dramatically at higher flow rates. Pressure limits of your pumps and channels become constraints. And at very high frequencies, droplets don't have time to fully form before the next one starts. Now let me tell you about surfactants. These molecules are absolutely critical for stable droplet microfluidics. Surfactants are molecules with one end that likes water and one end that likes oil. They adsorb at the interface and dramatically lower the interfacial tension. More importantly, surfactants prevent droplet coalescence. Without surfactants, your beautiful monodispersed droplets will merge back together within seconds. Surfactants can reduce interfacial tension from 50 millinewtons per meter down to 5 or even lower. This increases the capillary number by a factor of 10. For completeness, let me mention the Weber number. This becomes important at very high velocities. The Weber number is defined as ρHO U squared L over gamma, where ρHO is density, and L is a length scale. It represents the ratio of inertial forces to surface tension. When the Weber number is much less than 1, surface tension dominates, and we get the squeezing regime. This is typical for microfluidics. When the Weber number exceeds 1, inertial effects become important, and we can get jetting and complex breakup dynamics. Let me give you a concrete, real-world example. Suppose you're making an emulsion for a pharmaceutical formulation. You need 20 micron diameter droplets, and you want to produce 1 milliliter per hour of emulsion. Volume per droplet is 4/3 pi r cubed, with a radius of 10 microns. That's 4.2 times 10 to the minus 15 cubic meters, or about 4 picoliters. 1 milliliter per hour is 10 to the minus 6 cubic meters per hour. Dividing by the droplet volume gives 2.4 times 10 to the 8th droplets per hour. That's 67,000 hertz, or 67 kilohertz. This is extremely fast, and you'd likely need parallelization with multiple nozzles to achieve this. A critical concern in droplet microfluidics is stability and uniformity. You need consistent droplets over hours of operation. We measure uniformity by the coefficient of variation. For good monodispersity, you want the standard deviation divided by the mean diameter to be less than 5%. Many factors affect stability. Temperature changes alter viscosity and interfacial tension. Pressure fluctuations from pumps cause frequency variations. Channel fouling from particles or adsorption changes the geometry. Let me give you some practical design considerations if you're building your own device. Channel depths are typically 50 to 200 microns. Shallower channels give better aspect ratios but higher resistance. Deeper channels allow higher flow rates but may give less uniform flow. The orifice width in flow-focusing devices is your main control knob for droplet size. Make it adjustable if possible during prototyping. Material choice is important. PDMS is easy to prototype, but can swell with organic solvents. Glass is chemically resistant, but harder to fabricate. Silicon offers precise features, but is expensive. Let me compare the two main geometries we've discussed. T-junctions are simpler to fabricate with just perpendicular channels. They work well when the dispersed phase is viscous. Flow focusing gives better monodispersity and works over a wider range of flow conditions. It's better for high-throughput applications. T-junctions can easily make droplets larger than the channel width in squeezing mode. Flow-focusing droplets are typically smaller than the orifice width. Let me summarize the key equations you should remember. The capillary number, mu over gamma. This determines your operating regime. Droplet volume, approximately QD over F. Simple but powerful for quick estimates. The scaling law, D over W proportional to phi to the 0.3 times Ca to the negative 0.3. Let me leave you with some final practical tips from experience. Always use fresh surfactant solutions. Old solutions can lose effectiveness due to degradation or contamination. When optimizing, start with low flow rates in the squeezing regime and gradually increase. This helps you find the stable operating window. Monitor your droplet size and frequency over time. Drift indicates instability that needs addressing. Keep your channel surfaces properly treated. For oil and water emulsions, you want hydrophilic channels. For water and oil, hydrophobic surfaces work better. Let's wrap up with the key takeaways from this lesson. Droplet formation results from a delicate balance between viscous drag, interfacial tension, and pressure. Understanding this balance lets you predict and control droplet size. The capillary number is your most important, dimensionless parameter. It tells you whether you're in squeezing, dripping, or jetting mode. Flow rate ratio and interfacial tension are your primary experimental knobs for controlling droplet size and frequency. Both T-junctions and flow-focusing devices are valuable. Choose based on your specific requirements for droplet size, throughput, and monodispersity.